Around. And in the afternoon, we will have two exciting tutorials, Mujoko, headed by Hubo and his team, as well as OpenSim by Scott Depp and his team. And please also sign up for those tutorials that we can adjust rooms. Yes, Chris?
Am I correct that Mujoko is going to be entirely in Rashid in this room, and OpenSim is going to be entirely in 6115?
That is the current plan, but it will depend on how many people sign up. Okay. Okay. If you don't have any questions, oh, you do.
How do we sign up for it?
Okay, at the registration desk, there is sign-up sheets. Many of you already signed up yesterday. So please fill out by lunch. Okay. Oh, Steve wants to mention that we will be very strict on the time budget. So there are 10 and 10 talks, which means you have 10 minutes for presentation, and then we would like to allot 10 more minutes for discussion, because the point of this meeting is to have a lively discussion. And, I saw a hand.
So it's good if you sign up for the OpenSim tutorial, but if you don't sign up, you can still come. We're going to do it anyway. You can show up. And, it's not a big barrier.
Please sign up. And one last announcement, the tutorials fade out into a study hall section where you can continue on your own. But then at 8 p.m. we have a program manager session where George Chu from NSF, as well as Gil Pratt from DARPA will present about the latest developments and opportunities at these respective agencies. Okay, without any further delay, I will hand it over to Pranav and our first keynote speaker, Jun-Ho.
Good morning, everybody. Welcome to Pittsburgh and to Carnegie Mellon University. It's my pleasure to introduce our first keynote speaker, Professor Jun-Ho Oh. Professor Jun-Ho received his bachelor's and master's from Yonsei University in Korea in 77 and 79. He followed the Ph.D. from University of California at Berkeley in 85. He's currently the Distinguished Professor of Mechanical Engineering and the Director of the Humanoid Robotic Research Center at Korea Advanced Institute of Science and Technology. Now, in the past few years, he has developed an impressive line of humanoid robots like the Hubo II, and the latest one, DRC Hubo.
Hey, Prof.
Yeah.
I think you don't have to be so loud. You
Thanks,
can
Andy.
move the mic away a little bit.
Okay, I'm almost done. So please help me welcome Professor Jun-Ho to Dynamic Walk.
Oh, there's one. Can you hear me? Thank you very much, and I'm very happy to be here. When I came here, I thought that I must be strange here because I never been in Dynamic Walking Conference, but I found Chris, he invited me actually, and I found my colleagues, and I found my old student here, and the Anthony Kuo, Professor Anthony Kuo, and Georgie Chu. I met many friends here, so I'm very happy, and also it's my honor to be here. And when I was asked, when I was asked to give a talk in dynamic walking conference, my immediate thinking was that, what is dynamic walking? Because I'm always telling that the robot is dynamic walking, passive walking, but for me, it's very hard to make definition what is dynamic walking, because we already discussed a lot what is definition of dynamic walking. So since past several years, I forgot. I tried to forget what definition of dynamic walking, just walking, okay? So, and I recall me that I have to say what is dynamic walking, but still I decide not to say about what is the definition of dynamic walking. And so I would like to start my talk with that some of you are not quite familiar with the humanoid robot itself, so I'd like to introduce the history of my development of Hubo robot. And also I'd like to try to spare at least 10 minutes for discussion, because 10 system here, so I'll try to start my talk before 10 to 10. Okay, I studied humanoid robot work in about 10 years ago. This was my first version of humanoid robot named KHR1. It doesn't have any head and has, so his name is Korea headless robot. Actually, humanoid robot, but sometimes someone called me headless robot. And next year, we made KHR2. It's already, it does have head and hands, but still HR. And human robot, and it does have visions and autonomous walking and batteries and the wireless control and everything. So it is truly human robot, except beautifully exterior. So in next year 2004, we made KHR3 platform named Hubo. It became a first Korean human robot, and the second after Japanese other human robot, like ASME and HRP2 series. And the next year, we made this one named Albert Hubo. The name is from that his face by accident look after Albert Einstein. So I started to call him Albert Hubo. And he can display some facial expression through the movement of the head skin. There's some episodes there. It is not my work actually. I asked him to build this one for me. His name was David Hansen. He's a very famous guy to make such kind of Android type heads. And by that time, still now, most of the Android robot face look like very beautiful lady usually. But if you try to make very beautiful lady, it's possible. But it's very hard to make her beautiful smiling, beautiful laughing, and things. So if you fail to make very beautiful expression, she just look like a zombie, or just very, very strange, ugly looking. So to prevent that kind of uncanny valley, so I decided to make this kind of very wrinkled face, an old man. See that his eye is not symmetric, and his mouth is half open, but it's quite natural looking. If a beautiful lady is doing something, very, very strange. So it is very, so we wrote paper for this, that we just go over uncanny valley with this kind of naturally flow face. And this light is camouflage because his head is big man size and his height is about 1.3 meters. It's a big head and short like guy. So it looks very strange, but we put very big shoulder case with the flashing lights and it confused audiences. So it looks very natural, relatively natural. See, that is my invention. That kind of idea was my invention. And this one is another thing, is we call Hubo FX1, is Bigfoot type things. It could carry up to 150 kilos of man, and it can be controlled by joystick. And yep, this is without case. And recently we make Hubo II. Difference between original Hubo and Hubo II is that weight. So original Hubo was close to 70 kilos on his weight, but this one weighs only 44 kilograms with case and batteries and 2 computers, everything. So 30% lighter than the original one. That means that it could move faster and it could run more with single charge. And it could run with the light body. So I believe that this is one of the lightest one, actually lightest one in this class of robot at this moment. And it does have force torque sensor to measure the contact force between the ground and vehicle. And it does have a gyro sensor, inertia sensor, three gyros and 3 accelerometers. It measures the attitude of the body. And it does have 3-axis force torque sensor on its wrist to measure the external force. And it sees the camera and some speakers and microphones so it can communicate with the external world. And this exterior. Okay, this size is about 1.3 meters, and the width is something like that. This ratio is the whole ratio is I try to have more anthropomorphic, so this ratio is quite similar to about 15-year boy or girl, or 12-year maybe. And this degree of freedom. Each leg has 6 degrees of freedom. That's the minimum number for bipedal walking. If you have more, then you can make more natural, strange motions. But if you have 6 DOF for each leg, then you can make natural, the human-like bipedal walking. And we have 3 axes in shoulder and 1 axis, and 2 axes, sometimes 3 DOF in the wrist. And we have 5 fingers, and each finger moves independently. And each finger is passive tendon. So I will show you. And we have extra joint for trunk rotation. So, and we have 3 DOF of movement of heads. So heads is usually nod, tilt, and this way rolling, no, the sway. And this one is saying no, but sometimes this kind of motion means that ambiguity. So some guy do like this way. I don't do if can I say yes or no, but yeah, Hubo could do that kind of gesture. This is chest part. There are chest part does have batteries, computers, and 2 arms must be attached, and heads must be attached, and this pelvis part should be attached. So it's box-like, very strong box-like, very solid, very very tight, not solid, very tight, and all the limbs are attached from that trunk box. And arm, its length is about 22 centimeters each limb, and it can fold up to this much. So like as and it's very light. It weighs only 3.3 kilos. 3.3 kilos. And this one shows movement of arm. Because the weight is 3.5 kilos and moment of inertia was about 30% compared with the original one. It means that it could move arm very in high speed. So it demonstrates, this video demonstrates the kind of things. And this one shows how it makes drum hitting. As you know that drum hitting is quite hard because it's quick start and abrupt stop. And it should have some compliance. So combining those kind of things make it possible to do such kind of whipping motion with drumstick. And this demonstrates how wrist hand is working during handshaking. So if the gas moves and it follows his motion through the first torque sensor. And this one demonstrates push-up motion because we like to test how strong the arm is. So we asked them do some this kind of push-up motion, and he succeeded to do that. And another one is that we took out arms from him that we extend the length and how we test how it moves and how can it be have some kind of function, do task. And this is actual hand for him, and this is actual speed, not accelerated one, just one-to-one speed. As you see that it moves very friskly and fast and smooth. And also we tested a similar experiment. We took out hands and asked him to hit the ball, and this maximum acceleration speed was about 900 degrees per second. It's quite fast. And it reaches the final speed reaches up to not the 100 miles per second, but at least 20 miles per second. It's quite fast. And this is a hand. This one is we took the hand out. It weighs only 380 grams and the 5 fingers, but this is all mechanical. So I would like to show you how complex is it that this is part before assembly. All this part is for pair of hand. Okay, so there are so many the pulleys and bearings and shafts and the ball bearings, the general bearings and shaft and cables, and 5 motors for each, and those parts, and very small springs on the fingertips and everything. If you assemble it and use so that kind of very small neat finger, this one shows how the finger is moving, and it weighs only 380 grams. I should bring it. Usually I bring that hands for my presentation. I forgot to bring it. Because the finger is under-actuated, so it is shape adaptive. Well, once it's grabbed, shape is not determined until it touches the objects. So objects touch, then it forms naturally to have that forms. So there is no control, only current feedback. So each finger has certain level of current. So if a current level is higher than stronger grip and lower than very gentle grip, so it's very, very easy to control. And this one shows how to move in 3-way actuators on the wrist. It's shaking. And this head part, it does have 160 camera. You can put more, but we put at least one camera. And this head neck movement is 3-way, as I mentioned. And it is microphones and speaker somewhere. Okay, see that how it moves. Okay, this hip joint. Now we are going from top to bottom, and hip joint is 3-way. One axis here and 2 axes coincide in one point. So 3 axes meet at one point. So movement itself is ball joint-like, but manipulability is not 100% all the way, but it moves like a ball joint. So there are many ways to construct 3-way movement at one point with the servo driving. It's selection of the designer. For example, say here, the arrangement is different, and this part, pelvis part, we put penanty at the same point and rotation. This one prevents singularity during walking. And the knee joints here, it could bend up to this much, so the hip joint almost hit the heel. Okay, so you can completely fall down and to the ground. So this one demonstrates how to pick up the ball from the ground. Okay, this one demonstrates the single leg support. This one is in the air. Looks, he's doing, I cannot do that, but he's robot, so he's keeping the position very in steady position. So this shows that, it proves that he could climb up the stairs or ladder. So one leg could support his whole body weight. Okay, and foot, as I mentioned you that we have three-axis force sensor, and we put compliance here in between in the foot and the ankle joint. Because if it is too rigid, and any kind of walk, it's very hard to get the control. Because it's too rigid, then compliance control is almost impossible because mechanical gain is too high. So we have to intentionally put some kind of compliance. So we can select the stiffness by choosing the material of this one. We use urethane, such size. We change the size, then you can change the compliance. Stiffness, spring constant of that part. And this one shows the moving the range, and this is the torque limit. You may not be interested in the weight distribution. And thus far, I mentioned the mechanical parts. Now we have control parts. So we have two computers inside. One of them are at least Linux or Windows XP, doesn't matter. We now use Linux for controlling. So real-time control is done by Linux. And the other one, we have same computer. The other one is equipped with the Windows XP. And two computers are connected into very simple serial lines. So the left one is handling all the hardware, walking and motion primitives and stabilities and everything. And the right one is completely empty. So if you bring your own program, it's an intelligence program like Visions or any program, then you download into that computer and giving the command through that very simple serial line, like go forward, go backward, left, right hand, left hand. So it gives some kind of motion primitives. Then you can make this robot intelligent with your own program. And this one is hardware structure. We have many subboards. Each one, all of them are connected with CAN line, control area network protocols. And main CPU sends the signal every 200 times per second for the commands. And we have here is motor boards and sensor boards and inertia motor boards and finger boards. So if you call it one agent, it does have about 20 agents of his body. So they're communicating 200 times per second and make the system as a one with the main computer. This one shows joint controllers, how it works. They are all smart. It does have LEDs here, so it can show you the current status. It is smart board, so you can control the linear interpolator. It's a simple CNC machine, so it adapts all the kind of the high-level commands directly. So each one drives up to 500 watts for each. So you get 2 channel times 500 watts maximum. And we have 2 channel, 3 channel, 5 channel, and all different purposes. So what's the noise? And this is force sensor, 3 axis, and it also measures the orientation. So noisy, orientation and angles and everything. So the inertia sensor is installed here, and temperature sensor. So it can detect the inclination when it touches down the ground. It can measure the inclinations and slip. It has rate gyro, so it slips, then you can detect the slippery. Okay. The noise is from the CNC machine because our lab does have 2 the machining center there. So all his machine is running. So we took this video when machine is running. So the noise are from the machining center. Believe it or not, actually Chris saw that we produce all the parts in my lab directly. So we have 2 technicians. They are running the machine all the way, and we cut everything. and we produce all electric boards and everything. So we bought from outside that what we got from outside is motor and gear elements. We built everything in my lab. So it accelerates the development speed because, for example, say if I want to make this part, I draw 2D drawing, and my staff make a CAM program, and next hours he give me the products. It will take 5 hours. It's faster than RP machine. So it's very, very effective in many cases. And this is power boards. And it is such kind of complicated machine because this machine handles about 40 motors at the same time. In very squeezed area, it is not fixed all the joints. There are more than 40 joints. So everything is squeezed on this base. And introduce many electric inductive noise. And also it shares the different voltages, 48 voltages, 12 volt, 5 volts, and 24 volts, all different kinds of voltage levels. And each line drives different currents, and the current dynamic range is very, very high. When it stops, it's zero current. It starts move and peak at 20 and plus by 20. So it's very, very noisy environment. So power handling is very critical. So we call smart board. So it regulates, measures all the voltage all the time, and it regulates the situation. So for example, say turning on the power without this kind of thing, it has so many sparks inside because there are very big capacitors. Each board has very big capacitor, for example, say. If you apply the voltage, current directly, then it draws very big current at very first time. If you have that kind of 10 or 20 or 50 capacitors in parallel, these big sparks is coming out. So you have to be very, very careful not to burn the boards and connectors and everything. At first experiment, we burned connectors every time. Every tunnel, go on and just stuck and never turned off and burned next time. So now we have very good boards, and we solved everything. And with power monitors, so the smart board measures, monitors the power levels and power consumption, voltages, and displays. And just one switch, on and off switch is handling everything. And this remote switch could do that. And battery is lithium polymer battery. Now we recently changed to lithium ion battery. Its capacity is about 400 watt hour. And maximum peak current is 60 amp. You could drain very big current. And to test that how long could Hubo work with a single charge of that battery. So we put one battery with single charge, and they let him walk until it dies. And we check the time, and he's walking. See, 1 hour and 20 minutes. Okay, still is walking. And 2 hours, still walking. And 12, 15, 14 minutes, is going to die. Yeah, okay. Until before dying, it runs about 2 hours and 40 minutes. And this is, he walks about 2 kilometers during the time. So his walking speed is about 1.5 kilos. No, just 1 kilometer per hour. Not very fast, but anyhow. And we check the time consumption graph, and we check the temperature. And 1 minute, 10 minutes, and the last minute, temperature not go over 35 degrees in centigrade. So it means that it's quite acceptable, and it draws very reasonable mild current in the average. The peak is high, but in the average, and it generates hits in a moderate way. And thus far, I explained the hardware structure of Hubo. Now we have to talk about real dynamic walking from now on. Okay, so to realize walking, you should have two. First one is you should have so-called central pattern of motion. So once you walk is made, then you program each movement of joint to produce that it is not falling down. That is the pattern generation. And once pattern generation is made, you can play back that motion to the robot, but that does not mean that robot is walking, because timing might be different. Say you program to touch down, but if you not touch down the ground, then you have to wait until touchdown and restart again. That timing problems, and it might be touched earlier, or it might be touched down in a different way. You have to recover the body. So that is called online dynamic walking, online walking control, dynamic walking. So two parts. So first you make pattern generation and realize walking with that kind of control. And I checked several walking examples. This is ASME. Okay, it's the very first version, but his walking form is not quite changed. He's walking gentle, pew, pew, pew. And this is HRP, a very famous one. It's bent knee, knees quite many bent. And this is the drunken man or pet man sometimes. And it's always, it's truly dynamic walking. And this Hubo walking, I'm going to talk about straight knee walking. So there are, if you see, for examples, the walking pattern is a little bit different. In the case of ASME, his walking is quite elegant sometimes, a little bit bent, but his walking is gentle, something like that. And I imitate. I'm not quite good actor, but and in the case of HRP, usually he has very heavy bend, because HRP is designed to do some physical work with the man. So his first thing is that keeping stability. So he tried to lower the center of mass and try to keep in level of moving. So his moving is something like that. And in Petman case, he's very amazing. He's dynamically stable. So there is no statically stable point. He should have balance all the way. So he's look like a drunken man, but he's quite advanced, I think. And also he used straight knee. So he's just look like he's very close to human walking motion. And Hubo itself is straight knee also. In pattern, straight knee and bent knee is quite different approach. It depends on the applications, and also it heavily affect on the stabilization control later. To realize the walking, the static walking, dynamic walking, same. The problem is quite difficult, because say this one is robot. Say robot is usually K. Theta is given, then in task space X is made. Okay, that is typical robot. You give joint command and you will get the actual task. And to give this one, you got kind of inverse kinematics, and this motor controller. Usually what you do is that in task plane, you give X reference. In task plane, you got the posture, the position of robot. That is a very usual way for the anchored robot. So because his ground is anchored, so you give X command, then you get X reference, you get X. But in the case of humanoid, there is no anchor point. So this one is we call floating base robot, because every command is given from the trunk or pelvis. Okay, they're all reference from the pelvis. So this one is given relative to the floating base. So if you see the movement in the world reference, inertial reference, the movement is quite different. That makes everything very, very difficult. So how could you get the position, task position in the task plane? There are two ways. We measure the force torque when you touch down the ground. So if you see that value carefully, then you can estimate the posture. So if it is touched down straight away, then there is no moment, then okay, there is no moment is applied, then you can guess, you can estimate the pose. Another way to get the pose, they put inertia measurement system. So combining inertia measurement, you can guess the pose of floating point, and you can guess the status of feet is in the air, is touched down, it got some inclined. You can guess that kind of thing from this measurement. So you combine all those measurements, you have to modify the X reference to get your final value. So if it is still down, And then if you send the signal, but the posture is changing, floating body is changing, you have to recover, re-send the signal to have your original purposes. So to perform this one, the connectivity is not constant. Sometimes you have to switch this one, switch on, switch off, and on. There are so many switch on and off in the case of it in the air, so you have to ignore, say first signal. And if you touch down, you have to use. And in some case, when you touch down the ground at first, you have to apply positive feedback. So you have to form the touchdown, this foot. And when you touch down the rock, and you have to allow him to move like this way. Once he's firmly grabbed the ground, then you have to do position control. So there are so many switches, and when the switch is on and off, it's all variable structure. So the control gain should be changed all the way. And sometimes force control, sometimes position control, and there are alternately, very quickly, during the single step is made usually in 0.7 seconds. You have to do everything in 0.7 seconds, on and off and on and off, and control and stabilize and everything, making pattern and stabilize. So it's very short time. So usually in control, usually we're talking about steady state, but in walking there is no steady state, all the way transient. Before getting the steady state, we have to change it. The other leg is coming out. So control is very, very strict and tight in reality. So we have to combine pattern generation and the position control. I would like to first explain walking pattern. So many of you may hear about GMP, zero moment point. If we assume that this kind of very simple pendulum, inverted pendulum, then the GMP is something like that. It's combining inertial force plus the gravitational force as they combine. So this direction, this point is GMP, and this is reactive force. So the GMP is might be expressed like this way in a very simple form. If you see that if this L is very small, so this mass is about this point, then, or how can I say, L is very small, or this acceleration is very small, lateral acceleration is very small, then XC, and this is central mass and GMP is same. If this lateral acceleration is big, then GMP moves a lot. So this GMP is related with this value times acceleration. But this value, if you see carefully, that is reciprocal of the natural frequency, usually. Means that if smaller robot and medium and in human case, this value, natural frequency value, is 1 hertz to 0.5 hertz. And this the L over G value is something like that. And actual step frequency for each the one, for example, very small Aldebaran robot is usually this walking step size is something like that, 2 times a second. In the case of man, you are the expert of this, and usually 1.5 hertz to 2 hertz, usually. It depends on the step size. But in the case of human robot, usually a little bit slower than the human, because it is difficult to get the higher speed. And so you choose somewhere around this region. And so once you decide step size, then you have to decide. In our case, we define several things. They are very familiar with the single support and double support and things. And we define that one. And another assumption that there are so many ways to design the central pattern. There's someone called GMP-based design. Most of them are GMP-based, but there are 2 ways: the forward way and inverse way, and 2 ways. But basically, it is GMP-based. But for me, I couldn't sleep very well yesterday night, so I was short breath. I take the 5 more minutes for breathing. Sorry. Sorry. The jet lag, due to the jet lag, I couldn't sleep yesterday night, so I have a little bit short breath, so I have to drink a little bit of water. This is mine. there are several ways, the analytic solution and parametric method. In the case of Hubo, I use parametric method. That means my assumption, my speculation is something like that. Human is walking. If you see, you're the expert over there. If you see the joint movements, there must be very simple harmonic. That's my assumption. If there is no jerk motion, means that it must be very simple, the quadratic or cubic function. Or if it is sinusoidal, it's first or two or third, the harmonics is maximum, because we try to use minimum energy all the way. So it's a swing, just very natural swing walking. Each joint is very natural swing. So if we decompose that motion, emotion is mostly like this, all the way this. So I try sinusoidal and cubic functions and everything. I found that there is no big difference in between. So we decide to use the sigmoid function, and we use two types of function, sigmoid and the 1 plus cosine theta type things, and cubic function. If you draw that line, they are very similar in many cases. If you set up, sorry, I have a little bit of heart problems, I guess. So sometimes I should breathe if I don't sleep well. Okay, so then in that case, if you choose the period, amplitude, and the time of double supported and time of single support, if you decide the 3 or 4 parameters, you can completely design the shape. Okay, and then next one is that try this pattern to the robot and check the GMP. If GMP is acceptable, then okay. If it's not acceptable, you change the parameter all the way. Once you get the one set of parameter, then you can scale that one for the different type of different step size. So if you have some kind of table to extend the interpolate the series, then you can get reasonably good working pattern. So without that, if you solve inverse dynamics and everything, there are kind of the time series line. It is very difficult to scale and parameterize that one. So if you assume that the pattern is very simple parameter, it might be the cubic or the quadratic or fourth order, fifth order, it doesn't matter. But if you increase the order, then there are many parts in the acceleration. So I found that cubic is quite reasonable to assume that motion. And the analytic motion is given from function also. It's very simple because you assume that the GMP stays in line in left and right feet, then you can naturally get the motion of center of mass like this way. But thing is, the question is that is it good choice to have the GMP in fixed position on the feet? This is another completely different question, because when you observe the walking of robot, we don't see the position of GMP. What you see is that the position of center of mass. So if position of center of mass is swinging too much, it looks very unnatural. So if for man, say we alternately changing the foot, but we try to stay this body in center. It shift. It depends on the speed. If I move very slow, it shift plus minus 5 to 10 centimeters. It moves faster. We can narrow that one. It depends on the X2 dot and L G type things. Anyhow, so if you do have more natural shape of center of mass, you better design first. First, you give the position of center of mass, and then check first give the center of mass and try to find the GMP position on that movement. If you found that that produce the out of or the boundary GMPs, then you modify this one. So because usually the inverse dynamics may not have solution, so you have to find the solution iterative way. So you can get some kind of optimum value, optimum shape of the movement of central mass and GMP certified together at the same time. So there are two ways, but basically, as you see that they give GMP and try to find central mass. And second thing is give central mass and try to check that the GMP is in right position. So you can choose one of them. But if you do this kind of thing, it is very difficult to make the system parameterized. So it is not scalable in many cases. At last, you have to make kind of very simple function you have to make. That's better to be implemented in real working. Okay, this one is generated pattern of 30 centimeters. Okay, next one is the dynamic working controller. How could we stabilize all the robot? Sorry. Sorry. I forgot I have microphone here. I used too much time. And I'm always talking blind walking. Blind walking means that walking with prescribed pattern only. For example, say, if I blind my eyes, I could walk, assume that this is the flat and my assumed surface, okay? If I feel that there might be steps, then I have to be very careful. So blind walking means that walking with prescribed pattern. What I do is that all the stability is done by the blind sensor, like as first torque sensor, inertia sensors. So if the natural plane with some very small obstacles or very small inclination, I could walk without knowing the shape of the surface. So in a certain level of roughnesses, I can cope with original prescribed surface. So that is blind walking. So in blind walking, all the stabilization should be done by sensors. So if you do have non-blind sensor, like a vision sensors, non-blind sensor is sensor to foresee the geometry of surface so that for the robot to be ready prior to lose stability. For example, say the proximity sensor is the blind sensor because once it touches, then you fall down too late. If you have the blind sensor, you have to be very careful. Very careful. But you have blind sensor to foresee. Okay, I stop, change, okay, lift. I can plenty of time to modify the prescribed motion. So I'm always talking blind walking. So the sensor is covering all the uncertainties in the blind situation. So for example, say in force torque sensor, inertia sensor is working for that. And so in non-blind sensor is changing the pattern, and blind sensor is stabilizing during walking. So the most typical blind sensor is force torque sensor and proximity sensor and inertia sensors. There are several hierarchical ways to stabilize. We call one category is walking pattern control, and second category is real-time velocity control, and third category is predictive motion control. And real-time velocity control it should be done in real time. For example, the damping controller, single-phase GMP controller, soft landing control, upright position, all of it. I will explain one by one. And predictive controller is, for example, say landing position controller. It must be we have to predict the way that I'm falling down this way, then I have to move my foot on that direction. It's predictive way. And this walking pattern control is like it's in the average way. So if you walk inclined surface, you gradually change the central pattern. So there are three categories in the case of Hubo. And first one is damping control, for example. I would like to show you the result only. Okay, this is single leg support situation. Okay, this position locked. position locked naturally. If it is pushed, then it vibrates because it is compliancy here naturally, and there is very few damping. So if you push, it is pushed, then it vibrates very long time. Damping ratio is 0.01 or very small. So with this, if you allow this one during walking, it will fall down very easily, just and this way fall down. So you have to do some control. You will see that in the same external force, it will stop. So no residual vibration. One difficulty of human robot is that if you have human robot without control and try to push, okay, try to push, and it oscillates like this way, like that body. That frequency is about 1.2 or 1.5 hertz. That frequency is exactly matched with step the duration. So that's the reason that if you do some, try to walking without damping control, it just very easily, and it reduce the inward, increase, very small, it resonates all the way. You may have experienced that. So that's the reason that we have damp out very heavily, not to have that kind of exaggerated motion. If you don't have any such kind of damping control, it just moves like this way. If you reduce the sway value, then it stops. Very, very sensitive against with the sway value. So I will accelerate. I skip all the parts. Okay. But for example, this one is same thing. So without control, it oscillates like this way. And that frequency is sometimes very matched with the step, resonate with the walking step frequency, then it will get, you will get some. And then it's out of control, so it is damping the motion. That's very critical. Another thing is that this kind of phenomena. So if we have one leg lift, and this, you push, then it oscillates because it's flexible all the way. Okay. So if it is moving, it touch down this way, and this fall down this way. If it this way, it fall down this way. So by chance, it's always moving. It's quite random. Touch down. So it must be very, very steady all the way. So we have to do very heavy damping control there. So you saw, oops. Okay, you already saw that how damped out, right? Put off and on. You saw already here. It's off, and after turning on, okay, so it damped. It should be damped out in 0.4 seconds because every step is made in 0.7 seconds. And landing upright, and we have cope with all such kind of situations. And another one is landing position control. Means that if you feel that my body is moved this direction, then I have to shift the landing position a little bit that way to prevent that one. So that is landing position control. And this one is we measure the pelvis movement in phase space and try to keep in the original shape to make that one. So it is done by average way. So you have to try to keep that one. So if the center is shifted, then we have shift this way, backward to shift that way. So you try to keep that shape all the way. Okay, there are many things, and straight knee walking. Okay, that is close to the passive walking. So I found this one. Some of you already did. I have reference here. And how could we realize this kind of passive walking in real human robot? It's quite different because naturally it does have very high reduction ratio of motor on the knee. So we have to simulate that kind of when look the natural passive looking like motion. We have to simulate that one. So we have to how could we implement that one? The key is that if you try to solve the inverse kinematics problems, then you will get singularity problems when it's stretched. So all those solutions should be made in joint level. In joint level, thus far, we make all the movement, it was generated in task plane, in knee joint position is something like that. But in passive walking, when you design the pattern, you design the pattern of joint directly. Okay, that is the key. Sorry. Okay, yep. And I will show you the only video. Of okay. And this is the first experiment. And okay, you see the results. And this is a 2D walking machine. So when you design pattern, we first test with this platform. And there's a pattern. Okay. So this one is big. It's 40 centimeters. You see that the toe kick and heel strike walking, very natural. The natural straight knee walking is demonstrated. And also, we found that the energy consumption is about half. That's good. And then we realized it in 3D walking with this machine. As you see that the walking is quite natural like a human. And then finally we implement the same thing to Hubo. Okay. Okay, this I left this one for discussion. So you may raise questions, then I can continue my challenge for the robot with these things.
Use the mic to tell your questions because then the audio will not, the AD will not capture that, and also the rest of others who are far away will not be able to. So, questions? Confidence going on to the mic. Any questions? You start the right, Scott.
Thanks for your nice lecture. My question is about, for your straight knee walking, how straight do the knees actually get? Are they still flexed 10 or 20 degrees, or do they, like humans, reach very near full extension?
Actually, we allow very small band. That's for safety reasons. But it doesn't matter. Because during the swing phase, we do not use knee joint anyhow. So we do not allow any spin effect like a human. We do not use, just we use straight. For robot is possible.
The question is somebody good.
Hi, it's really amazing what you've done, and I work in biological systems and humans walking, and I probably don't fully appreciate how hard it is for you to do these things. So let me say that my question might be naive, but when I was thinking about when I see all these humanoid robots that are now very popular on YouTube and so forth, I see often them walking on treadmills. Okay. And what strikes me is that if you put a human on a treadmill, there's some very specific things that might help you to design a humanoid robot. So for example, if you take a very extreme case, if you put a human on a treadmill and you ask them to close their eyes, what happens?
I don't know.
They within 1 or 2 strides, they fall off the back of the treadmill.
Yeah.
So what does that tell you? That tells you that your proprioceptors and your vestibular sense gives you very poor absolute position sense of where your body is. And I wonder if you're designing a humanoid robot, should you take these very extreme examples from humans that tell you something about how to design the sensors? That you absolutely need vision to walk on a treadmill as a human. And many of these robots, I don't think they have vision when we're walking these treadmills. So that means their proprioceptive and inertial sensors are doing something very different than a human does. Let me give you one other example. There are a few people in the world, very few, who have no proprioception from the neck down because of a disease to their nervous system. Those people are in wheelchairs. They cannot even stand up with vestibular information. With vision, they can very poorly. So I wonder when you're approaching a humanoid robot whether you should take these very extreme examples from humans and say this is how we need to design our sensors if our idea is to design a humanoid type robot.
Okay, as I mentioned to you that in Hubo walking, we assume blind walking. So the pattern is already made. Blind walking means that pattern is correct, and then floor is something like that I design. The only thing is that the blind feedback. So and for vision, okay. So in the human robot, they will have confused that definitely. Okay? And also, I think that in many cases, I'm telling that sometimes people tell me that robot is walking, but I don't. Many times I say that this Hubo is not walking; it's imitating walking. It's alternately changing the leg and do something that happen to be not falling down. We call walking, but it's not natural walking. It's forced to move like this way. Looks natural, but inside it's very complicated, very unnatural. So it is very hard to compare with the human motion. So it is imitating the motion only. So, for example, say computer is intelligent, artificial intelligence, real intelligence, is imitating intelligence. That kind of questions. So I'm not going to compare with the robot walking and human walking. It's completely different. And way of thinking, way of control is completely different. We try to use the inertia sensors and force sensors, but I think the way of using is quite different, I guess. For example, say printing motion. Say if I choose, try to modify the touchdown position a little bit when I'm walking. I don't know how human is doing because it is very hard to predict that value because very small, so it is not measurable. But human is doing somewhere. So even this way I can walk. Okay. I make intentionally confuse my inertial system. Human is doing, but the robot is impossible. Very, very high quality sensor could not find the way that is falling down.
So you showed a slide on state estimation, and you said I can use my force torque sensors in my ankles to tell where I am, and I can use my vestibular system effectively to tell where I am, but I never combine the two. I either use one or the other. And that surprised me a lot. And two questions come out of that. One is, at what level are you doing state estimation? Are you estimating the center of mass location or full body Kalman filter?
Okay, it's very smart question because I'm always confusing on the position. Because you are quite right. For example, say force torque sensor here, it is used only for damping out, not posture measurement.
Okay.
And the posture measurement, we assume that whole body is just one mass. That's it.
So what happens when you're walking on irregular ground or
Okay.
slippery ground,
Yep.
and you cannot rely on knowing the foot inclination? How do you estimate the
Okay,
center of mass?
so firstly, we are measuring the ground inclination. As I mentioned, that we have a tilt sensor on foot. So when you touch down in irregular ground, like this way, for example, we measure the ground inclination immediately, and then they compensate the value to the inertial sensor. So we try to get the right value theoretically, but in reality, there are very many misjudgments. Because, as I mentioned here, robot is balanced at null position. For example, say, all sensor signal out 0 is good one. That is equivalent point. For example, say, inertial sensor, if I stand up, all must be 0. So if I try walking, it moves around 0, all around 0. And thing is that, so if you measure the signal, the reliable feedback, say for example, this step down like this way, if you measure that, it's slightly plus value from 0, because 0 is normal. If it's tilt this way, it goes a little bit plus value. And then I move a little bit forward on that direction. That's my strategy. But the thing is that value is so small, if it is misjudged, it's 0 and actual value is little plus, but noise is this much, it can measure in minus. Then it must go this way, but it measures different way and that way. Means that it's falling down. So sometimes feedback is very dangerous in human robots. For example, say, thus, we made whole hierarchical structural control in the experiment and to write a paper. We used that one. We took a good picture of stabilization with that one. But for critical demonstration, I turn off all the control. Because control signal got the wrong value because it is balanced in null position or signal is around 0, means that it high, very high signal to noise ratio. It's 0 and say the actual signal is 0 plus minus 1, 0.1, but noise is perfect 0.5. You combine two, then you got very wrong polarity. It's completely different. So you should have very, very high precision. Sensor is needed. The rough sensor couldn't do anything. You should have very, very good sensor, not to have any kind of noise. Almost ideal noise. I think that Boston Dynamics are using that kind of sensor. People do not have it. It's too expensive.
Okay, so one last question, and that should be from that side of the room, because there are so many questions coming from this side. Maybe that side, nobody? Okay. Maybe two people. Maybe I'll make both of you go for the question, so you can ask it handily.
Usually we think of zero moment point robots as ones that are balancing using ankle torques.
Right.
But you have all this other balance, foot placement, upper body placement, and so on. Could your robot walk if you turned off the ankle motor during stance?
No, I don't think so. Impossible. Because to do that, we have to use upper body like as moment compensation, reactive moment by moving like as windmill motions.
Also foot placement.
The foot placement is one thing, yeah,
But it's not enough.
not enough. Because that values, yeah, if it is possible, then we could use very small foot or big foot. So we try to. I think Boston Dynamics do that kind of thing. They are successful.
Yeah, you can use the mic to ask the question.
Oh, okay. Thank you. So my question is that I'm wondering how much of the passive dynamics of your system you are using to control the system to work.
I don't understand your question, but I'd like to say that, say, the small robot is 100% steady. Steady walking means that it could stop any time during walking. And the fully dynamic means pinpoint walking, like something like that. Let's say it's a full dynamic walking. I think the Hubo is 80% steady, 20% dynamic. Okay? The over same. Or the human robot is, I think, 70 to 80% steady and 20% dynamic. So dynamic part is very, very short, very short. So almost steady, actually.
Okay, so it's 11:05. We have a very short coffee break. Be back in 5 minutes, 11:10.
Thank you. Thank you.